Hello, I'm going to make a video where I talk about numerical methods. I happen to be taking numerical methods right now. I think the full class title is maybe like numerical methods in physics or something. Uh, the textbook's something like numerical methods in science and engineering, something like that. The basic idea is so most of the time in math class you learn to solve problems rigorously by manipulating the math symbols to come up with an exact answer. And you use certain constants to make the answer exact. So the answer might include pi, it might include I, it might include e, and so a lot of times though you're going to want to just use an approximation technique instead of an exact technique. Some examples are either it's too hard to solve the rigorous way. Say if you have to do the calculation many times, and so you'd really rather have a computer do it, then converting using numerical methods lends itself to using approximation techniques lends itself to converting it to computer code. And sometimes there is no way to solve the solution directly, so you have to use an approximation technique. So for all those reasons, you might want to do this. And basically, I'm just going to go through an example. So in our book, they're going over more challenging math examples, but these are ones that I didn't know outside of the book, so I figured I wouldn't want to use one of those because I'm probably just going to end up copying what's in the book. So I thought I would use something a little more basic. So we're going to use Riemann sums, and this is still from calculus, but it's from Calc 1, and I'll kind of give the basic idea. It's not complicated. So let's say we have your xy axis here. Ooh, that's terrible. Try that again. Okay, that's not so bad. Alright, so xy, and I want a parabola that I contrived a little bit ahead of time to make it all work out a little nicer. So let's say we have this parabola, and it happens to go from 0 to 4. So this would be the point 0, 0, the point 0 or 4, 0, and then the midpoint just it happens to be that the peak is at the midpoint, and this is going to be 2, 4, which normally you wouldn't know this ahead of time, but I happen to know it ahead of time. And the function for this is y equals, let's see if I remember, I think it was negative 4x squared. What did I write it down at? Negative x squared. Negative x squared plus 4x. Yeah, so this is our equation that we have. And the basic idea is, let's say you want to find the area under this curve. Okay, you can use a process called integration, which for this particular problem is relatively easy if you just know the steps. Or even if you didn't know the steps, you could use this other technique, which is actually what we're going to use now. So first, I'll do the integration technique, since in this case it happens to be really easy anyway. So this is the integral from 0 to 4. We're going from 0 to 4 of f of x, which is negative x squared plus 4x dx. This is going to be negative x cubed over 3 plus, we'll just write it out, 4x squared over 2, evaluated from 0 to 4. We plug in 4 for this, then we subtract plugging in 0, but plugging in 0 is not going to matter because it'll all become 0. So we can just plug in 4, call it a day. So we have negative 4 times 4 times 4, that's 4 cubed, over 3, plus the 4 and the 2 cancel, so we're left with 2 times 4 times 4. Then to make that so we can add it with the bottom, we have to multiply a 3 and a 3, and nothing's going to cancel out, so we have negative 64 plus 12 times 4 is 48. That's not going to be the way I want to do that. Let's try this way. 8 times 4 is 32. 3 times 3, that's 96. I like that better. So we got 96 over 3. This will be 32. The bigger is the positive. 32 over 3, which is approximately equal to 10. Oops, it was exactly equal to 10 and 2/3, which is approximately 10.6 repeating. So this is the solution that we are trying to get as close as possible to. Now, the technique that we're going to use is called using Riemann sums, and the basic idea. Let me grab a couple different colors here. Let me start with red. So we're going to split this up, and for simplicity's sake, we'll start by splitting it up into 4. So there's one, there's one, there's one, there's one. So let's say we split this up into 1, 2, 3, 4 sections, and then each section we go from the midpoint. There's different kinds of Riemann sums. We're going to use the midpoint version. And midpoint, the midpoint, the midpoint, and then we take those midpoints and we draw rectangles going out to, I think green didn't work out very well. Let's try purple. From the midpoint to the ends. So now well, you kind of have to use your imagination a little. I'm sketching this by hand. So now if you can see there, those purple rectangles approximate the area that was under the curve. They're close to it. You can see that they're not the same because there's like a little bit hanging out over the edge, and then there's also a little bit missing in these places. But the basic idea is it's close, and what happens is the skinnier you make these rectangles, the closer, the more accurate the approximation is. So the skinnier the rectangles, the more rectangles there are. Now to write this out in the notation, so it would be, well, let's just write it up here. So we'll call this area, because that's what we're looking for, equals the sum from I equals, well, it would be A. No, sorry, 0. I equals 0 to n of f of x sub I star, I'll explain that in a second, delta x. And what this is saying is that you sum together for starting from I equals 0 to n. Yeah, we should go from 0. Where n, actually in this case, yeah, this is a to b. I equals a to b. Fairly certain. This is 4. Yeah, so I could have said I equals a to b. Anyway, I wrote it out this way. It's good enough. So basically what happens is we take this f of x sub I star means this x point. So we go with this x value, this x value, this x value, and this x value. And we're going to take 4 of them. So that's why I actually can't think off the top of my head whether it would be from 1 to 4 or 0 to 4. I think it should be from 1 to 4, but anyway, then that's not a really big deal right now. So my point isn't really to teach this notation. Yeah, so this f of x value should be the y coordinate here, and the y coordinate here, the y coordinate here, the y coordinate here. And you'll see that those represent the heights of the rectangles. Now if we take each height and multiply it by delta x, which is the width, it's the change in the x value, that is the width of each rectangle. And if we sum all those up, then that's our approximate area. Basically, that's what this means. And if you wanted to write, yeah, my point isn't to teach that. So basically, that's what this means. So what we're going to do is we're going to convert this approximation technique into computer code using MATLAB, which you can still call it computer code. So you could do the same thing in a more traditional programming language. It would be a little different though, because for loops are kind of a little strange in MATLAB, but that's what we're going to do. So yeah, so what else do I want to say before we get to that? So basically, to explain what's going to happen here, once again, we're going to take since this, I picked nice numbers on purpose. So here we see that this is the x values. This is 0, 1, 2, 3, 4. So this is actually 1, 3, wait, no, 1, 2. So this is half. 1 half, 1 plus a half, 2 plus a half, 2 plus a half, 3 plus a half. So what we're going to have is f of half times delta x plus f of 1 plus a half. This is 1. This was technically 0 plus a half, plus f of 2 plus a half. Oops, I was supposed to say half. Plus f of 3 plus a half. And you'll notice I forgot to write every time the delta x. Each one of these should be multiplied by delta x, but the reason I forgot is normally what you do is if all of those are multiplied by delta x, you can actually factor it out and say delta x times the whole thing. And when you factored that back in, it would be delta x times each term. So anyway, that's about as clear as mud. And then what you'll see here is these relate to our a values. So it's a plus the midpoint of a. So our first x value is our first a value, which we're going from 0 to 4. So it's 0 plus a half, 1 plus a half, 2 plus a half, 3 plus a half. And then the, anyway, that's good enough. I think that kind of gets the point across. That's what's happening with this. So now that we know what happens, we can turn this into computer code. And so you can see what we're going to do is we're going to take we're going to say the area is going to equal, so the sum of all of these times delta x, or the sum, I don't remember how I did it last time, or I'm not really sure how I'm going to do it this time, but or as I started to write, you could write f of 1 half times delta x plus f of this would be 3 halves delta x plus f of no, that's, hold on a second, 2, 4, 5 halves. No, that's 2 plus a half, my bad. Yeah, 5 halves. 5 halves. Okay. Plus f of 7 halves. Okay, those should be alright. And I did it again. times delta x plus f of 7/2 times delta x. And so you can see here is these increment regularly, these x values, and every time you do the same thing, and then you just add it to what you had previously and build a total. Basically that's what we're going to do. And now I think I'm probably ready to go to MatLab. I don't think I need any of this, so let's go to MatLab. So I already made this function here. Literally I just, whoops, I don't want to do that. You click on new script, it'll pop up like this but blank, type function, whatever you want to name it, parentheses, whatever you want to pass in as input parameters, hit save, and then it should automatically come up letting you save it as this name, but if it doesn't, you have to type in the name, this name, and this name must match. Then it will need an end at the end, so it's nice to go put that in now. Basically that's where we are right now. So to write this code, we want to first, let's see, I'm going to start with the for loop, just because that's the part that I find to be a pain in the butt. So in MATLAB, for loop, we're going to say, you'd often say I equals, and then you need your start point, your end point, and then your spacing size, which actually lends itself very nice to this problem. There'd be, I think the code would end up being a little longer if you were doing it in traditional PC code, but we can go ahead and set it up as a matrix. So this is going to be delta x, which we haven't defined yet. I'll do that in a minute. No, sorry, this is A, our first value. This is delta x, our spacing, and this is B. So now we know we need to define delta x, so delta x, the spacing, is going to equal, it should be the absolute value of A plus the absolute value of B divided by N. Double check my notes, yeah. So absolute value of A plus the absolute value of B, and we'll just leave it there, divided by N. Express the output. So that's good. Now another thing we want to do, we're going to make a container that we're going to use. I'll call it sum, set it equal to 0. This is going to be the running total that we have for our number of divisions, like for our running total as we sum together each of the rectangles that we split it into. So this is like the running total for the total sum of the rectangles. Which means I'm going to want, at the very end, I'm going to want it to calculate the area, which I'm going to say area is sum times delta x, and then display area as our final result. So now inside the for loop, what I want to make it do is say, let's see, we want it to run the function, which I'm passing in the function as f on I. We want to suppress the output, and we can call this I started with I because that's normally what's used in computer programming, but in this case it does represent x. Technically it represents x star for our midpoint value. So I guess I probably was pretty good. We'll call it x star, since that's what it would be if you were to write out the Riemann sum formula. So x star. Now, let's see, there was something I missed. What did I miss? I was just thinking there was something I missed. Oh, I was just going to explain these up here. So what we have is function. This is the name of our function that we just created. You wouldn't have had it created as a function, but it's a lot nicer. It's a little easier. These are the parameters we're passing in. F stands for function. The first time I recorded this video, I typed in the word function, not thinking about the fact that function is a key word right here, so you can't use the word function. So I used the letter f that represents a variable that will be a function, a, which represents the starting positioning, the leftmost point that where we're trying to find the area, b, which is the rightmost point, n, which is the number of divisions. And we would have seen, had I finished writing it all out, where's my mouse? So to write this out more fully, we would say the integral from a to b of f x dx equals the limit as n approaches infinity. Is it n? We'll go with that. I think that's right. Anyway, I should have looked this up ahead of time. I may make a mistake on this. I don't usually use this sum notation a whole lot. 0 to n of f of sub I star delta x. So anyway, that's close unless I made a mistake. But the basic idea, though, the reason I wrote that is, so the point is, as n approaches infinity, we get closer and closer to our true value, which is why I wrote this out. That's really what I wanted to say. And so just relating everything again, this f is our function, which is going to be the function that represents this graph, which is y equals, we won't need the y equals, but it's going to be negative x squared plus 4x. Then the next thing we pass in is a. A is 0, our first x position that we're concerned with. You could have started anywhere. You didn't have to start on the x-axis. I just chose to make it look prettier. You could have started anywhere. We could have started at x1, and it would just cut off this portion, and it would only consider this as like a straight line up and down. Then we pass in b. B is the final x position, which is 4. Then we pass in n, which for this example that I drew, the first time we do this, we'll try x equals 4 just to see what it is. Then we'll try to make x a really large number in our n. We'll start with n equals 4 to show what if we were to work this out manually, everything I wrote right here, what that would be if you were to do that on a calculator. But we can then do it again where we make n a really high number and see that n should approach this value, which is the true value. And then once we know our system works, and because I know that the theory is solid, we could apply it to other integrals and solve them as well. I probably won't do that in the video, but it could be done. So let's see, did I miss anything here? Delta x, I don't think so. Sum starts at 0. We run through the loop on the, you know what, I needed the sum down there. This is where we need to add the sum. So I think we say, actually I think we can do it right here. This needs to say, every time we run the iteration, we need to add to sum. So we'll say sum equals sum plus. Now that's the reason that we started with sum equals 0, because, let me space this out to make it look better. The first time through, sum is 0. There's no sum yet. Our container is empty before we start the iteration. Then the first time through the iteration, we calculate this right here represents our first height, our height of our first rectangle. So now we add that height of that first rectangle to 0 and put that in the container, because we're basically building up like the total height, I guess. Then we go through another time. If n is 4, which is what we're going to start with, we would go through it the second time, find out a new value for our height, add our new value to our original value, and then store all that in the container. Then we run through it a third time, find our third height, add that to all the other junk that's already in the container, then we do it a fourth time, and then we're all done, and that's the total sum. And I just called it sum. That's the things we're summing together. And then to find the area, we multiply that total sum by the width of each rectangle. When the width of each rectangle is delta x. So that's going to give us our area, which the area is what represents the integral. It's what the integral represents, is the area. So let's go ahead and run this thing. These are a little bit weird to run. I'll do it all in one line. There's multiple ways to do it. And so this took me a little bit actually, because all the stuff we're doing in our book and in our homework and stuff, we don't actually usually do them this way. We usually use a while loop and just set it equal to true and have it break when it's done. I think the reason for that is because, so this is actually operating on a matrix, and so I believe we need to use the matrix operators, which I'm going to use them. And if they're redundant, I apologize, but I think we need them, so I'm going to use them. It's one of the weird things about MATLAB that for me it's been really hard to get used to, since I'm a little bit used to regular programming languages. So to call this, we just type the name, Riemann sum midpoint. We pass in the parameters. So f is our function. Our function was, so to pass this in as a function, you can't just write, you can't just straight up pass in a variable, like a variable. So they're all variables in computer term, but you can't pass in a variable in math terms where the variable changes during like the process. That's not crystal clear, but that's as clear as I can think of to explain it right now. So you start with an @ sign and you declare which one's the variable. So we'll call it x because I like x. You call it anything, and then you write your function, which was negative x squared plus 4x. So it would be, I'll just write it normal first and then edit it. Negative x squared plus 4x, and then that would be the end, so we put a comma. But what we want to do here is this negative x squared, we want to put the matrix operator, and MATLAB has to have a multiplication sign in between, like the x's. You can't just put things right beside each other. And I think that's all we need. So that should be good for a function. We have a as 0. That's our leftmost point that we're concerned with finding the area of. The rightmost point is 4, and I set n to be 4 initially. So if we run this, it would tell us what we would get had we manually calculated those Riemann sums. 10. So 10 is our approximation for the area under this curve. And 10 is actually not too far off from 10.6, which is kind of impressive considering we only did it 4 times. You could have done that by hand and it would have taken 5 minutes probably, especially if you're really familiar with the process. But let's see how much closer we get to 10.6 repeating if we do it a lot of times. So you can press the up arrow to bring the last thing you typed. So the only thing we want to change here is n. So we had it at 4. Let's try 400. I actually don't know how long I can go before I break it. Let's just try 400. Well, that's 10.66 repeating already. If I go format long, we can see see more decimal places. Actually, I don't remember if it rounds or if it just truncates it, but it looks like it truncated it. So let's try running that again. No, it actually did. Okay, it did round it. So it happens to be 10.6666 with a bunch of zeros and then a 3, and who knows what's after that. So that's pretty close already with 400 iterations, but let's just kind of go more for the sake of, I don't know, I'm not sure how much my computer can handle. So let's go 4,000. I don't even know, would we get one more 6 out of that? We have 1, 2, 3, 4, 5. So we have 5 6s, and the next one is really close to a 6. The previous one we had 4 6s, so going 3,600 more iterations just gave us one more 6. I think that I'd have to jack it up really far to even see any more results, but So you see now that how numerical analysis works, and there's a little example of doing Riemann sums. So now, actually, if you had some integral and you wanted to check your answer, I mean, in modern times, you can just go to Symbolab or whatever online for free and type it in, and it'll like solve it for you. But if you didn't want to do that, you could make this thing, and then now, if I wanted to check my work, I could just throw in my equation and my a and b, and then some really high value for n, and get a really pretty accurate answer, and then compare that with my true answer that I get from solving it the more rigorous way by using calculus. I mean, this technically uses calculus, but not like, it's not the same. I don't know. Maybe I guess this doesn't technically count as calculus. Anyway, it's a little bit weird. You know what I'm trying to say, I think.